It's pretty amazing when you think about it. Our bodies are basically electric. I mean, we're talking tiny, tiny signals that tell our muscles to move, our hearts to beat, everything. But what happens when those signals go haywire? Well, that's what we're digging into today. We're going to explore these incredible tests that let doctors literally listen in on our internal wiring. It's all about decoding the body's electrical language to figure out what's going on with nerve and muscle diseases. And so often, this whole story starts not with a test in a lab, but with a person, a real human story. A lot of us know about ALS because of the baseball legend Lou Gehrig, right? When he was diagnosed, it suddenly put this devastating, really mysterious illness right in the public eye. It's a disease that just attacks the very cells that let us move.
So that brings up the big question, the central mystery, really, for any neurologist. How in the world do you diagnose a problem you can't even see, especially in a system as ridiculously complex as our nervous system? Well, you've got to find a way to listen, to tune in to that electrical language the body is speaking.
Okay, so let's dive into the case we're cracking today. It's the challenge of diagnosing weakness that just comes out of nowhere. You can really think of it like a detective story. And the clues? They're these super faint electrical whispers coming from deep inside the body. So, what are we actually talking about? The big category here is motor neuron disease, or MND. It's kind of the umbrella term for all these conditions. The best way to think about it is like a slow progressive failure in the communication line, the one that runs from your brain all the way down to your muscles. And ALS, that's the most common and unfortunately the most aggressive form of MND. All right, to really get this, we've got to meet the two main players, the two types of motor neurons. First, you have the upper motor neurons. Think of them as the command center, the CEOs up in the brain. Then you've got the lower motor neurons. They're the messengers, the couriers that take the orders from the command center and deliver them right to the muscles. Now here's the key. Damage to the command center causes one set of problems, like stiffness. But damage to the messengers, that causes stuff like weakness and twitching. And to diagnose something like ALS, doctors have to find proof that both systems are in trouble. So how do they find that proof? Well, the first thing they do is check the wiring. And the first tool they pull out of their toolkit is the Nerve Conduction Study, or NCS. I love this analogy. It's basically like an electrician coming to your house to test the cables, just to make sure the signal is getting from point A to point B without any issues. And check this out. This is what the results actually look like. These squiggly lines, these waveforms, this is literally the language of your nerves printed out on a screen. On the left, we're looking at a muscles response, and on the right, a sensory nerve signal. So let's break down what we're seeing here. Okay, that first waveform on the left is called a CMAP, a compound muscle action potential. Here's how it works. Doctors send a tiny, safe electrical pulse down a motor nerve, and then they measure how the muscle reacts. And the key thing they're looking at is the height of that wave, its amplitude. Why? Because that height tells them exactly how many muscle fibers got the message and are doing their job. So, a smaller wave, that means fewer fibers are working. Simple as that. Now, the other one, on the right, is a SNAP. This one measures a sensory nerve. And here, we're not so worried about the size of the wave. We're interested in its speed. How fast is that signal traveling? Because that speed tells us all about the health of something called the myelin sheath. It's basically the insulation on your nerve wire. And just like the wiring in your house, if that insulation gets damaged, the signal slows right down. Okay, that was the NCS, checking the wires. Now for the second major tool, the EMG, or electromyography. This one takes the investigation to a whole new level, because instead of just testing the nerve wires, the EMG listens directly to the muscle. For real. It's like sticking a super sensitive microphone right into the muscle to eavesdrop on what it's saying. And this is what that tiny microphone picks up. It's called a motor unit action potential, or MUAP. You can think of this as the voice of one single motor unit. It's the sound of one of those messenger nerves firing off an order and its little squad of muscle fibers contracting in response. And believe it or not, the exact shape and size of this little blip holds some major clues. But here's where it gets really fascinating. It's all about what the muscle is doing when it's supposed to be doing nothing. See, a healthy muscle, when you're just relaxed, is totally quiet, electrically silent. But a muscle that's been cut off from its nerve supply, a denervated muscle, it gets irritable. It starts firing off all these tiny, random electrical signals all on its own. It sounds like static on a radio. And that sound, that static, is a huge red flag for active nerve damage. But you know what? Our bodies are incredible fighters. When some of those nerve fibers die off, the healthy nerves next door don't just sit there, they try to pick up the slack. They literally start sprouting new connections to rescue those muscle fibers that got abandoned. And this whole repair process creates a totally different sound, a much more complex, kind of choppy waveform. It's actually a beautiful thing to see, because it's a sign that the body is actively trying to heal itself.
All right, so let's recap our detective kit. We've got the NCS, which is checking the main highways of the nervous system, and we've got the EMG, which is listening for that telltale static of damage, but also for the hopeful sounds of repair. The whole game is about putting all these different clues and patterns together to finally solve the puzzle. And for a really serious diagnosis like ALS, doctors don't just guess. They use a very specific framework, kind of like a checklist, called the L-Escorial criteria. They are systematically hunting for evidence, proof of damage to both the command center neurons and the messenger neurons. And they have to find this proof in different parts of the body, like the arms, the legs, the trunk. The more places they find trouble, the stronger the case becomes, and the more certain the diagnosis. Okay, but this brings up a really important question, right? How good are these tests really? I mean, can they actually tell the difference between something common, like a pinched nerve in your back, and a much more widespread disease like ALS? And the answer is a resounding yes, they can. And every single bit of it, comes down to the pattern. Think about it. With a pinched nerve, what doctors call a radiculopathy, all that electrical static is going to be found only in the muscles that are connected to that one single pinched nerve root. It's a local problem. But with ALS, the problem is systemic, it's widespread. So the EMG will find that same static in totally different parts of the body, supplied by completely different nerves, maybe in an arm and in a leg. And that's the smoking gun that proves the issue isn't just one pinched nerve. So look, these tests are, without a doubt, incredibly powerful. But we have to be realistic. Like any tool a doctor uses, they have their limits. They're not a crystal ball, right? They're just a way of listening for evidence. And sometimes that evidence can be really subtle, or it might not have even shown up yet. And one of the biggest limitations is all about timing. Timing is everything here. As you can see, the clues, the electrical evidence of a nerve injury, they don't just pop up overnight. It takes time. That static we talked about, the sign of active damage, can take a few weeks to get loud enough for the EMG to even hear it. So you can see the problem. If you do the test too early, you might miss the diagnosis completely. And this, of course, leads to the chance of what's called a false negative, where the test says everything's fine, but it's not. For something like a pinched nerve, for example, the numbers show that even with a really skilled doctor, the test can come back totally normal in about 20% of people who actually do have the problem. That's 1 in 5. But, and this is a really big but, on the flip side, when the test is positive, it's extremely reliable. The chance of a false positive, where the test says there's a problem when there isn't one, is super low, only around 5%. So here's the bottom line. If the test finds something, you can be pretty sure it's real. But if the test comes back clean, it doesn't give you 100% all clear. It just means there wasn't enough evidence to hear yet. So in the end, these tests, this whole field of electrodiagnosis, really just blew the doors open on the hidden electrical world inside all of us. It took what was once a total mystery and turned it into a solvable case, all by teaching us how to just listen. And it really makes you wonder, doesn't it? As our tools get even better, as we get better at understanding this body electric, what other incredible secrets is our nervous system just waiting to tell us?